Thank you for joining this Zurich Instruments webinar on fast-tracking your sensor development. Hi, I'm Jim Phillips, application scientist with Zurich Instruments in the Boston office. I'm happy to be joined by my colleague, Kıvanç Esat, product manager in Zurich. At Zurich Instruments, we are excited to be part of this global environment, learning from each other and from you, our users. Our instruments are used with sensors from a few hertz up through the RF microwaves and with devices requiring fast feedback. We have learned many lessons from working with these devices. Kıvanç, can you tell us how we put these lessons to use in helping our users speed up their sensor development?
Of course. Thanks, Jim, for the introduction, and also welcome from my side. As Jim mentioned, so we have many customers actually already using our instruments for their sensors applications, and we aim to share this with you and also hope to inspire you in your next sensor development challenge. During this webinar, please ask your questions in the Zoom chat that you can find in the platform. You can write them anytime. We will try to answer as many as possible at the end of the session. And then we will also answer them in a blog post at a later time. So with this, we can continue and start our presentation. We would like to start with a very basic question, actually. How does a sensor work? A sensor, essentially a device that creates an electrical output that is somewhat sensitive to the quantity of interest. That could be temperature or a magnetic field or any other physical parameter it could be. As I was listing earlier, so this is basically a very wide range of parameters that we can probe using sensors. That could be mechanical, that could be environmental properties, material property itself, like conductivity, the phase of this material, or magnetic field strength, to name a few. And looking at certain forms of this sensor could take, it can actually be a tiny product if it is a MEMS or an AMPS device, for example, that could fit to our daily lives, being in our smartphones, for example, or it can be a large project that would aim for a unique measurement that in the end we can publish the results. But what it takes actually to create a new sensor in the end, with this entire perspective that we just briefly looked at, the workflow is actually quite typical. Starts with finding the correct material. That could be a nano device, a thin film, a particle that is actually levitated, for example, a different kind of materials such as dielectrics, piezoelectrics, or so. That's where we do spectroscopy, transport measurement, scanning probe microscopy-like techniques to understand how these materials are actually behaving. Once we understand the actual interaction that we are looking at, the next step is designing the sensing element based on the principle we discovered and characterize its behavior. That is calibration, that is impedance measurements, looking at the linearity to find the optimum operation conditions. And this is done by parametric sweeping, impedance analysis, and so on and so forth. The next step is to ensure the sensing element that we just characterize is operating at the right conditions, right? And this comes with a control and the correct readout circuitry around it. So this boosts our stability, the response time. We can ensure that the device works at the right operation mode. And this is typically done by feedback controllers. And the next step, before we can actually bring the sensor to use, would be packaging it and ensuring that the sensor that we produce, maybe in bulk or maybe just a few, has the right quality. And this comes with the right confidence before doing this packaging, designing the ASIC circuitry. As you can already guess, this is actually an iterative step. In anywhere in the field, in a scientific or research field, nothing is linear like this. We need to go back to the drawing board, reiterate various things. And what's the key here is that the effective tool set that will enable us to go through these iterative steps quickly so that we don't lose time when we need to set up our measurement setup. So let's go back actually and look at how this sensor, how to capture the sensor's response we just looked at. As we discussed that we are looking at electrical signals the sensor converts us to. And the key here is to preserve this information content. And very often we use lock-in detection for this. This allows us to capture very weak signals, as you can see as the blue signal here, the important information we need. And such a test instrument should be precise, should give us repeatable results. It gives us time and frequency domain control tools, and also should be flexible enough to do other things. Before moving forward, let's look at a few examples actually, what is actually measured in various cases. It could be a mass spectrum. In this case, it's actually a cantilever, a mechanical device here, where you can see some dots on it. These are actually added particles on it, one by one, and we measure its spectrum. And this will be the corresponding mass spectrum. And this is done by such nanomechanical resonators. Another example is an impedance-based sensing, for example, wearable devices, such as this person is wearing a strain sensor here, where the arm movement actually depicted as a change in capacitance. In a completely different end, we could also make sensors to measure gravity. These fellas, for example, here are placing long resonating beams to capture the gravitational pull with respect to each other. In another experiment, we can use levelated masses to actually detect small gravitational forces. So in its essence, these are whole huge different fields, but what do they share is one component. That's the lock-in detection that you can find in all the papers. So with this, I'd like to stop and actually give the floor to Jim, where he will explain how this lock-in detection works and what are the benefits that they bring to us.
Thank you, Kıvanç. And now let's take a look at what a lock-in amplifier can do for you. Why is a lock-in amplifier like listening to a wristwatch in the sound of a jet engine? Well, we do that with a lock-in amplifier. It's good at detecting tiny, tiny signals in the presence of large disturbances. Our job is to make the disturbances as insignificant as possible and the signal as large as possible to maximize the signal-to-noise ratio. So we begin that by looking at what is the noise and looking how it's distributed over frequency. So at low frequency, there is so-called 1/f noise, which is associated with drifts of various kinds, most especially temperature, and it's quite ubiquitous. At higher frequency, we have white noise, so the noise spectral density becomes flat in the frequency axis. And then there are synchronous sources which are associated with the power line frequency and with switching power supplies, and up at higher frequency with radio. So these signals are coupled to us by various means, capacitive, and by sharing ground paths and other means. So the very first thing we do with almost any sensor project is we shield. We put the sensor and it's the thing it's sensing in a conducting box, and that may or may not be more or less convenient, but it is usually needed. We use shielded cables or coaxial cables. And then the next thing we may have a ground loop. So if you have a ground loop, you have a bad current that's being injected by some other device. You need to identify what that is, what is the device, and then if you still need to have it switched on while you're doing your experiment, how can we route that current so it flows in a place where it doesn't disturb the grounding conditions of our sensor? And that's a process, but those are the steps. Where is the bad current, and how do we make it flow off to the side where it doesn't bother us? Now, the main tool we have after that, after we've taken those basic steps, is to modulate the signal, to choose our frequency so that we are operating in a range where there is not other noise. And it is modulation with a lock-in amplifier that allows you to choose your frequency. So the lock-in amplifier, to modulate the sensor, we apply a current to something like a Hall sensor, say, and we'll modulate the current, and we'll look for the transverse voltage on the Hall sensor in synchronism with that modulating signal. So that's the principle of a modulated experiment with a lock-in amplifier. If there's a resonance in the experiment, a resonator, then that provides a natural modulation, which you will quite likely use. And then if we manage to get the frequency right, then instead of at the blue fuzzy signal at the bottom, which shows the noise you get measuring at DC, we can get something more like the little red curve, which is measuring at a higher frequency, where we're out in that nice white noise region where the noise is fairly low and flat. Now, how does a lock-in amplifier do this? How does it separate that signal? It is by so we have this tiny blue signal in the left-hand red noisy signal, which is the signal we want to detect, and we need to measure its amplitude and its phase. We have with us the larger blue signal at the same frequency. That's our reference signal. So what the lock-in amplifier does is it takes that reference, makes a nearly perfect digital copy inside. These are fully digital lock-in amplifiers, and it takes a digital copy of the signal and it multiplies them with a nearly perfect digital multiplier. Now, when you multiply signs at F1 and F2, you get F1 plus F2 and F1 minus F2 in the result. In the lock-in amplifier, we usually make F1 equal to F2, so the difference frequency is DC, and that's what we want. That measures the amplitude of the sinusoid at that frequency. We then do this with a sine signal and a cosine signal, two signals 90 degrees out of phase. The resulting demodulated signals are called X and Y, and from those the lock-in amplifier will calculate for you the amplitude and the phase. The double frequency signal is visible in that right-hand set of noisy signal. And we need to take out the double frequency signal and the noise, and we do that with a low-pass filter. So lock-in amplifier can also work in what is called internal and external reference mode. In internal reference mode, the lock-in amplifier creates the signal and sends it to the experiment, which uses it to modulate the experiment. Other experiments wish to generate their own modulating frequency, in which case you work the lock-in amplifier in external reference mode, where the sine wave comes into the lock-in amplifier. Beyond the demodulator, in a fully digital lock-in amplifier, such as those provided by Zurich Instruments, we can demodulate at multiple frequencies. So we can measure a signal in its harmonics, measuring nonlinearity. We can measure at unrelated multiple frequencies, for example, the different modes of a cantilever. And Kıvanç will talk about an example of mass spectrometry on a cantilever, which takes advantage of that. And we can also measure at F1 plus and minus F2, which is natural when you have two modulation frequencies, F1 and F2. You might modulate a laser and have a cantilever, for example. It's also useful for Pound-Drever-Hall locking, which we'll talk about later. In addition to the multiple demodulators, the digital lock-in amplifier provides some other tools. It's easier by far to diagnose problems with the signal in the time domain and frequency domain of the input signal, not after the demodulator. The demodulator kind of hides the conditions in the real world, and it's harder to find out what's going on. So these lock-in amplifiers with the Lab 1 software provide an oscilloscope tool, which allows you to look at the input connector, time domain or frequency domain. There's a plotter tool. There is a general purpose parameter sweeper, which is extremely useful for setting up quick experiments to find out how things vary with a particular parameter. And then these tools are also integrated in the Lab 1 software with optional feedback controllers and even arbitrary waveform generators. So with that about lock-in amplifiers, Kıvanç, can you tell us more about what we can do with this software?
Thank you very much, Jim, for the nice introduction on how lock-in amplifiers actually work and what kind of information we can learn from them, and also what kind of tool set they can actually enable. And now I'd like to focus a bit more into these tool sets and what they provide us in terms of sensor characterization. The important first step is essentially to determine what's the right drive signal, what's the correct stimuli for the sensor to operate in the right parameter space. So the frequency response analysis is often used to characterize the frequency that we essentially determine the frequency that we need to drive the device or the sensor. In addition, spectrum analyzers or scopes, as Jim also mentioned, are quite valuable at this step. But determining the drive signal is not the only thing. We also have various parameters like bias voltages, certain drive amplitudes that we can also need to characterize and essentially sweep in a certain parameter space. And this is done by a parametric sweep. For instance, backbone measurements are addressed this way. Once we know how to drive the sensor with the right signals, also looking at its temporal characteristics is important, which we do by step response measurements. And the last but not least, characterizing the impedance of the device at hand is important, especially when we build the ASICs circuitry around it when we are packaging the device. And also the certain impedance parameters could be the measurement we are after. The tool set in sense of the time and frequency domain, as we briefly summarized, should work in the same box for the most efficient characterization workflow. This is what we actually provide with our Lab 1 software that is integrated with our lock-in amplifiers, as you can see here. And in a single screen, you can see all these measurements, and the most important is they run in parallel. Let's look in a bit more detail here. So the frequency response analysis we mentioned to determine the optimum drive signal in terms of frequency, right? And such a sweep could actually provide a response as we see here. This is a very common behavior of a resonator. At a certain frequency, the amplitude increases rapidly, and we also see a kind of a step response in the phase as well. And this is a behavior of a linear resonator. And then from this, we can determine the frequency, the bandwidth or the line width of this resonator, or the quality factor. They all reflect the similar property of the resonator itself, and also the phase delay at the resonance. And this is an important parameter, but we can also look at how the sensor behaves at different parameters I mentioned. For example, here we sweep the amplitude, and at some point when we increase the gain such that the device starts actually behaving nonlinearly. And this is what we actually see here. This is a great measurement to determine where is the place if you want to be in the linear regime, or when we can exploit nonlinear effects, for example. Step response, as I mentioned, is important. For instance, if you want to look at underdamped situation, as you see here by these fluctuations over time, or the overdamped situation where we see a rapid decay or settling the signal, as we observe here. Here we also look at the impedance analysis in a similar fashion. It's also a step response actually over a few femtofarads only of the change in the capacitance as a function of the stimuli that is basically a changing DC voltage, as we see here. And capturing these rapid changes in impedance precisely is quite important. For example, MEMS devices. So I already mentioned that actually the software is really important that binds all this together. That is what we achieve with the Lab 1 software. It's a powerful user interface that integrates all these toolsets together. You can do analysis on the fly with the fitting tools, with the trend analysis, for instance. And all these tools actually can run in parallel in one screen, if you like, also in multiple screens as well, or even your smartphone. Platform independence is important, such that this tool can operate in pretty much everywhere that is convenient to you. And integration at the software level with the programming libraries for efficient integration with the rest of your setup and automation, of course. With this, let's look for an example case, how we can actually turn these measurements into a sensor. So the first step we looked at was to stimulating the sensor with the correct parameters. And then the second is measuring its response with the lock-in amplifier. And the measurement parameters are typically amplitude and phase, right? Here we look at an example for a gas detector. Here we actually have the gas cell that we send a laser light through and look at the intensity of the light coming out from the cell. In this scheme, we are doing actually a tunable diode laser absorption spectroscopy, TDLAS, which is a great example of such sensing devices. We work with two signals that we generate. One is the sawtooth here. That is the DC bias voltage that tunes the wavelength of this laser diode that it generates. And then we have this ripple structure that is essentially the modulation that Jim introduced to us, that is used to demodulate the signal that we need to spectrally separate it from the rest of the noise sources or disturbances. A typical measurement then would be if at a certain frequency, while we are moving around this edge of the sawtooth, we see a dip in the spectrum, and this corresponds to the absorptions, right? And this we can depict as a spectral absorbance as well. And this is one of the commonly used ways in gas detection. But let's actually look now, what are the other ways to actually enhance the sensor's response or the precision? And with this, Jim, please take over.
So let's look a bit at what resonators can bring to this measurement. Frequency sensing is very commonly used with sensor work. A particle dropped on a cantilever you can measure frequency tremendously sensitively. So the particle dropped on the cantilever, and Kıvanç will talk about some of these later on, can shift the frequency enough that you can measure it. The frequency measurement can be extremely sensitive. Other experiments need to measure the viscosity, for example, of the material around the resonator, and so they measure Q. So there are several ways to measure a resonance. One is with a frequency response analyzer, in which the resonance needs to sit still, and the frequency response analyzer sweeps across the resonance and measures. By fitting afterwards, we can find out the frequency and the Q, the line width and the Q. There's a phase lock loop, which measures at a single frequency. It can be put in a feedback mode, as are the other modes that we talk about here, so that when the resonator moves, the resonator frequency changes, the oscillator follows it. And dual frequency resonance tracking uses two carriers, balances the amplitude, and Pound-Drever-Hall, which we'll talk about later, uses frequency modulation. It's this three-carrier arrangement. An example is superconducting microwave resonators used for quantum computing devices, and often one just studies the microwave resonator in order to optimize one's material process. What happens here is that noise in the resonator is very important to get to a minimum level, and the two-level systems that create the noise shift the resonator frequency and, of course, broaden its line width. It is important to measure at extremely low power in order to elucidate the two-level systems properties, and then to try to eliminate them. So with Pound-Drever-Hall sensing, we have a resonance, and we have a carrier, which is the middle, represented by the middle arrow in the Fourier decomposition of the frequency modulated signal, and two sidebands or more, and a purely frequency modulated signal has a careful balance between those three components so that the amplitude modulation component is 0. When this interacts with the resonator, it interacts unequally with the three and disturbs that balance. And so then we put in frequency modulation into the experiment, and where there's no amplitude modulation, out of the resonator. If the oscillator, if the carrier is detuned from the resonance, out of the resonator comes an amplitude modulated signal resulting from that imbalance. And we've been working on this. I've been working with a group of collaborators at the University of Colorado at Boulder to detect the Pound-Drever-Hall signal in a novel way. The normal method is to detect the amplitude modulation with a power detector, a diode or nonlinear device that gives us a measure of the power. But we've been looking at a different way. So the digital lock-in amplifier provides strong advantages on the receive and transmit sides of this operation. Generating the signal, you, again, because you want to measure at very low power to access the two-level systems, you want to generate the FM signal over a wide dynamic range, and the digital system can do that. The analog system tends to need recalibration at multiple power levels. On the receive side, the digital lock-in amplifier will measure those carriers directly instead of using the nonlinear detector. And we've given papers at the American Physical Society March meeting 2023 and 24, in which we describe this tendency. If you want to know more about this, my contact information is here, or you can just get in touch with us at Zurich Instruments.
Thanks a lot, Jim, again, for the overview on how to make use of resonators and how to track what they are doing, actually. Let's look back again to the workflow that we looked earlier on the sensor development process. So far, we captured essentially the first 2 points. That's the finding the correct material, understanding how it behaves, how it interacts with the parameter that we try to measure, and then how to design a sensor out of this. This also comes with the characterization steps. Now let's look to the next step, actually, where the control becomes important and what value it actually gives to us. So in the open loop behavior, as we call it, the stimuli is steady. So we find the correct frequency to work with, set our stimuli at this frequency, at the correct amplitude that we characterize, and this signal stays stable. But there are a couple of things can happen working in this configuration. For example, if we have a certain stimuli as such, it's quite hard to actually determine what it really does. But after a set point that we just observed, that's essentially the onset of the feedback controller, which gives us a set point. That set point that we fixes our device to be at, and the disturbances now actually becomes these sharp ripples instead of these big steps that we were looking before. And these ripples are much easier to determine, and we can do more precise measurements around this set point. in terms of how much amplitude, for example, this ripple gives us. The next is actually looking at the step response. If you need to weight the response of your device as sensor itself, the settling time will determine that, which is given by the line width, the quality factor, if this is a resonator device. We can accelerate it by feedback to make sure that after a certain disturbance, the device goes back to its set point as we enforce by the feedback controller. And this essentially makes our measurement time also faster.
Kıvanç, let me jump in here and define a feedback loop and show how we set one up on the digital lock-in amplifier. So I'll use a phased lock loop as an example. In a phased lock loop, we take an oscillator signal, we feed it to a resonator. The lock-in amplifier measures the phase coming back from the resonator, and that phase varies through the resonance, so it allows us to set our position with respect to that resonance. So we choose a set point, which is the phase that we'd like the phase lock loop to hold, and then we take the measured phase minus that set point. That is called the error signal. It is fed to a PID controller, which then adjusts the oscillator frequency to sit at the desired point with respect to the resonance. So now we say that the oscillator is locked to the resonator. This is the workflow in the digital instrument. We begin by measuring the transfer function of the device external to the lock-in amplifier, the device under test. So when we have that transfer function using the sweeper tool, we use its math tools to calculate the resonance frequency and the line width, and then we open the PID tool, and we tell the PID tool what type of a loop we wish to build, what are its input and output. We tell the PID advisor the numbers we got from the parameter sweeper, resonance frequency and line width. And now we press the advise button, and and the advisor comes up with some coefficients, which we then copy into the PID controller. And then we enable the PID controller. It should lock. So once you are in that state, you want to know if you're locked and how well you're locked. So there's a lock indicator. And if that's not enough, you can plot the resonance frequency as a function of time. The various tools you can use to test that lock. You can also test its step response by adjusting the set point abruptly. And that allows you to adjust the coefficients in this PID controller to optimize the step response to get it to be as quick as possible, but without overshoot or ringing. And you can fully adjust the loop. So with that, I'll ask Kıvanç to show us some examples.
Let's look at in a concrete example, actually, how a phase lock loop and in addition an amplitude gain control would give us. So here above blue is the amplitude over time, and the orange is the phase over time. And you see when there's no control, the signal is fluctuating a lot. It's not stable. We will first enable the PLL in a few seconds. And there we go. This is the onset of the PLL where we see a stable response that we can rely on. And here we actually turned on the automatic gain control that stabilized the amplitude in addition. And these two loops, they work in parallel, boosts our sensors' sensitivity and also the response time. Now we can move on to a few examples how these techniques we just heard of, the open loop techniques and the closed loop techniques, can be used in an application. In this case, we pick an optomechanical mass sensor example. We actually published an application note on this as well. You can find it on our website. And we will look at 3 distinct examples that look at different types of material to measure the mass. In this example, we have a particle in the trap. So this is an optical trap This is a counter-propagating Gaussian beam trap that keeps the particle here at the center when I am pointing my mouse. And we look at the motion of this particle, and we modulate this by changing the balance between these two lasers. And this modulation is demodulated using like an amplifier. And here, what the phase response actually we see as a function of the frequency. This is an overly damped harmonic oscillator actually, because the particle is in air, so it's quite a lot of damping coming from that. That's why we don't see a strong resonance, so it's an underdamped situation. But the phase response, you can actually model it as the force damped harmonic oscillation model, which is then giving an arctangent here as a function of the damping coefficient, the resonance frequency, and the frequency we measure. By fitting this and also predicting what the damping is on this particle, we can then essentially take out the mass of this particle that is inversely proportional of the damping we capture from this equation. And the benefit here is, of course, that the particles as such can get oversaturated, and we can measure the mass of oversaturated particles that is really hard to do in a beaker. Let's move to the next example. This is a completely different scheme where, again, a like an amplifier does most of the job in terms of the control of the device and also the measurement. Here we have a cantilever that is actuated. It's actually a resonator device which has multiple modes, which we characterize using frequency response analysis to get a sense of where the frequencies of these individual eigenmodes of this cantilever and what are the equality factors and how the phase response looks like. And now, after we characterize this, we want to track this phase using multiple PLLs that run in parallel on individual eigenmodes. What happens when we drop a particle, these eigenmodes changes, the frequency of these eigenmodes changes. And they all happen differently because depending on where the particle sits, it affects individual modes separately. And that's why we actually track multiple modes together. Here you see how the phase shift of 4 different eigenmodes happen at individual adsorption event. These are the steps responses here in the zoom in the image here. And then we can basically use this data to fit this equation here that's also coming from the equation of motion. And the delta F, the frequency shift, can be related to the edit mass. That's the delta M here. And the psi here corresponds to the mode of the mode shape essentially. And using this 4 parallel phase-locked loop measurements, we can depict the edit mass and also its spectrum essentially in femtogram resolution. And here you actually see these individual particles adsorbed on the cantilever surface. In a different example, and now we are actually looking at capillary particles, essentially particles in tiny microfluidic tubes, and we want to differentiate different particles. The one step could be, of course, measuring the mass, and we do in a similar way. We put the capillary in a suspended region here, and this capillary is then the suspended area is a double clamped resonator that is actuated here. And we monitor this actuation by the laser light that we impact on it, and then looking at the reflected light. The blue curve here is the amplitude, and the red curve is the phase response of such a resonator device. So it's a very wide resonator. The quality factor is not very wide. That's why we can also relate the delta F, the frequency shift when a particle passes, with the change in the phase directly, because the Q is not getting impacted much when a particle passes by. It is great because then we can directly have a measure of the phase, which we can then use to calculate the mass. But there is another problem here because we are essentially here sensitive to the buoyant mass, not the actual mass of the particle, because this is the capillary resonator and the colloidal particle. And that's why we use another technique that relies on optical scattering. And depending on how particle scatters, so the different material scatters light differently, we can also use the same signal line to look at the signal amplitude to also have an idea about the total light that is reflected or scattered. And this way, we can deconvolute this mass spectrum that we captured with the frequency measurement. We can deconvolute it using the scattered light, and then we see these nice distributions of different particle types. So basically, these three examples are showing how we can use various techniques on similar even systems to characterize and then control the sensor. With the next step, I will again hand it over to Jim, where he will talk about how we can actually measure the Q itself.
Thank you for those nice examples of control, Kıvanç. I'd like to add one more example of how we use control with PDH sensing to measure line width, or Q. So there are a number of ways to measure line width. You can use a frequency response analyzer, and there the resonator is supposed to stay at the same frequency, and you sweep across it. And so if the resonator frequency does vary during the frequency response analyzer measurement, then you get a false estimate of the line width, which is too large, and the Q is too small. And the resonator is most likely to move when you have lots of time to do the measurement, which is at low power, when the signal-to-noise ratio is low, and you need to integrate for a long time. So PDH gives us this second-order measure of Q. Detecting at the second harmonic, we get a direct measure of Q. And that signal is peaked at the center of the resonance, so it's going through a maximum, and to first order, there's no variation of that signal when the resonance shifts in frequency. But to keep the oscillator centered on that resonance, we can again use a feedback loop, sensing with the PDH. And that's how my colleagues and I have done it. And then you get a better measure of Q.
Okay, let's summarize what we discussed so far. We looked at why lock-in detection plays a pivotal role in sensing applications that allow us to capture a tiny signal from the sensor in a haystack that is large noise and disturbances. But this is only the beginning. The lock-in amplifier that offers the essential tool set to analyze the signal at hand with efficient workflows is also a crucial part. And we already discussed the iterative sensor development workflow, where this plays an important role. In addition, various tracking and control schemes are also required to ensure the sensor is operating as designed. Zurich Instruments lock-in amplifiers and the Lab1 software puts the tool you need at your fingertips with many aspects and streamline the many aspects of the workflow. But Jim, can you actually talk briefly about the other aspect that is really important?
Perhaps the most important part of Zurich Instruments is our people. We have PhD application scientists with backgrounds in many fields of interest to you who will provide premium support. We love to share our experience with you to help speed up your sensor development. Challenge us. Please tell us about your project.